All right, this is day 9 of our unit about exponents, and this is a review of the entire unit. Just a brief snapshot. We've worked with simplifying exponential expressions, solving exponential equations, graphing exponential functions, and using exponential functions to solve real-world problems, exponential growth and decay. So, here are some problems covering those topics. Let's see, first of all, recognizing growth and decay by looking at the equation. If you want to know if it's growth or decay, this is where you want to look, right here, the base. If this number is bigger than 1, then you are looking at exponential growth. So this would be, what am I doing? Okay, yeah, so this would be decay because that's less than 1. Now, 7 over 4, clearly that is bigger than 1. So that is going to be exponential growth. Okay, and 4.5 is also bigger than 1, so this is going to be exponential growth. All right, number 2, a signed baseball, $150, increases 6% value each year. Write an exponential function that gives the value after t years. All right, well, exponential growth works like this. The eventual value is going to be the beginning amount, times 1 plus the rate to the power of time. All right, so this is the model that we're using. So we start with that beginning amount. So the value is going to be $150, okay, that initial amount. And now we're going to do 1 plus that rate. Now, my rate is 6%. But when you write your rate, it has to be expressed as a decimal. So 6%, if we move that decimal point twice to the left, becomes 0.06. So that's the R value that we're talking about. That's the rate. So this is 1 plus 0.06 to the power of time. So this really is the equation, but let's not leave it as 1 plus 0.06. Let's go ahead and put it together as one number, which of course would be 1.06. Okay? Let's go ahead and skip ahead and answer these two questions. This R value as a decimal is what we call the growth rate. So the growth rate is 0.06. Now this number inside the parentheses, including, the 1, is what we call the growth factor. Okay, so the growth factor is 1.06. Anyway, if we want to find the value after 4 years, all we have to do is use this function and let t be 4. Okay, so let's just put that in the calculator. 150 times 1.06 to the 4th power. Okay, so in 4 years, it should be worth $189.37. Okay, number 3, the value of your new car, $30,000 car, decreases at a rate of 13.5% each year. Now, since this is decreasing, we need to use the exponential decay model, which is almost like the exponential growth model. We still have the beginning amount, but instead of doing 1 plus the rate, we're going to do 1 minus the rate. Okay? Now, this number 1 really represents 100%. So in the case of growth, we were basically starting with 100% and then adding 6% every year. So that's how we got 1.06 is really 106%. But since we're decreasing, again, this 1 really represents 100%. So we're starting with 100%, and from that we are subtracting, well, let's go ahead and write that decimal. This is the percent of decay, but the rate of decay we will write as 0.135. Again, moving that decimal point twice. So 100% minus the 13.5%, that's what we're really doing. Anyway, so our model, our function, is going to be that initial 30,000 times 1 minus the rate of 0.135 to the power of time. Again, don't leave it as 1 minus 0.135. Go ahead and do the subtraction. So yeah, 1 minus 0.135 is 0.865. Don't round this. Keep those decimals, and that's what we'll put in here. Okay, so 0.865. Okay, so that is our model. I should put a box around that. Okay, so again, now what is the decay rate? The decay rate is this decimal. What's the decay factor? The decay factor is this base here in the parentheses. Okay, 0.865 is the decay factor. Find the value after 5 years. I will just use this function and let t be 5. So that's going to be 30,000 times 0.865 to the power of, and we want to know after 5 years, so we'll let t be 5. So after 5 years, our $30,000 car is now worth only $14,527.86. All right, the 86 cents seems a little silly because it's an estimate anyway, but let's just go with it for now. 14,527. And I think it's at 86 cents. Yep. Okay. So there's that. I'm going to box this too. Okay, moving on. Number 4, you find an amazing investment that pays 13.2% interest compounded semi-annually. Man, I keep forgetting to change this. Last year we learned about compounding interest on different times, quarterly, semi-annually, but this year we did not do that. So I'm going to cross out the word semi, and let's just go with a more simple case for now. All right, we will save the quarterly, semi-annually, all that compound interest. In fact, I'll cross out the word compounded too. We'll do compound interest in another lesson. Anyway, so we're just going to do your basic model. So it'll be the initial amount of $5,000. This is growth. So I'm going to do 1 plus the rate. Okay, again, this percent, if I want the rate, I have to move the decimal point twice. So this would be 0.132. So 1 plus 0.132 to the power of time. And of course, I will go ahead and add these together and just put 1.132. So this is the model. What is the growth factor? Well, that's the 1.132. That's the growth factor. What's the growth rate? Well, that's this decimal, 0.132. How much money will we have in 5 years? Use this function and let t be 5. Okay. Okay, so that's going to be 5,000 times 1.132 to the power of 5. All right, so $9,293.99. Okay. Moving on. Simplify, leave all exponents positive. All right, so yeah, a lot of kids have trouble understanding how to simplify exponential expressions. So let's practice it one more time. Well, and looking at number 5, you know what, let me zoom in a little. You know what, in fact, let me do a quick review of the basic things. There are 3 basic cases that you're going to see. You're going to see things that look like this. Say if I have n to the 3rd power times n to the 4th power. Okay, that's one thing. And then you're going to see things like this, n to the 3rd power to the 4th power. Okay, that's something else. And then you're going to see things like this, like 3 to the 4th power. These are 3 different things. Okay, so let's just remember. How do we handle this first situation? This is when you add the exponents. All right, if you're multiplying with the like bases, you're going to add these exponents. So this is when you would add and you would have n to the 7th power. When you just have the base appearing once and you have a power raised to a power to where you could just circle these like that, this is when you multiply. So this would be n to the 12th power. But if we just have a regular number, not an exponent, just a number, then you have to actually do the power. So we won't multiply, we won't add. This means 3 times 3 times 3 times 3, which would turn out to be 81. Please understand that if these were actual numbers, like say 7s, we will not multiply these 7s together and suddenly get 49. Just like when they were n's, we had n, and it stayed n. When it's a 7, that base doesn't change. 7 to the 3rd power times 7 to the 4th power is 7 to the 7th power. Okay? And when you look at ones like this 3rd example, don't get confused if I add something in here, like if I put an x squared in here, that doesn't change the fact that it's 3 to the 4th power. With the exponent, I will wind up multiplying. That'll be x to the 8th power, but that 3 is still 3 to the 4th power. Okay, so those are the basic cases that you're going to see. One more thing you're going to see, remember, if you have a fraction, let's see, so say I've got x squared. Say if you have a fraction to a negative power. The way we handled that was we do the reciprocal. Alright, so I will turn this upside down and do x squared over 3 and then to a positive power. So that's what you do if you have a negative exponent on a fraction. And then you can go ahead and do the power. So this would be x to the 8th power, because power to a power you multiply. But this 3, I have to do 3 to the 4th power, so that would be 81, and that would be my answer. Alright, so that's just a brief review of the basic stuff that you see. Wait, as long as I'm doing a basic review, let me mention one more thing. Say if I have x y to the negative 3 power. If you have a variable or anything with a negative exponent, that tells you that the thing with the negative exponent is on the wrong side of the fraction. So that thing has to be moved. So if I have y to the negative 3 power, the y is going to move down. Notice that the x will not move with it. The x just stays where it is. So this would become x over y to the 3rd power. This goes down and becomes a positive 3. Okay? It would be the same thing if this were some number. Say this were 5y to the negative 3 power. The y goes down, but the 5 is going to stay where it is, up in the top. Say you had something else down here in the bottom. In fact, let me change this whole problem. Say if I had this. Say if I had y to the 4th power and down there, and I have x to the negative 3 power down there. Only one of these has a negative exponent, the x. This will move up, but the y has a positive power, so that the y would stay right where it is. So the x would move up and become x to the 3rd power, but then that's it. You don't move them both automatically. You just move the one that has a negative power. Everything else stays where it is. So this would be the answer. Okay, so now that's a good little review. All right, let's do the actual problems. So for number 5, we will multiply the negative 8 times the 4. So that's going to make negative 32. When we do p to the negative 12th times p to the 6th, that is when you add. That's the situation I mentioned. When you have the variable appearing twice, you add. So negative 12 plus 6, all right, that's just going to be negative 6. But again, if we have a variable and this negative exponent, that tells me that this is on the wrong side of the line. So I'm going to take this and drop it down. Okay, so then this is going to become negative 32. Whoa, why did I put a 3? All right, this is going to become negative 32 over p to the 6th power. Again, notice that the negative 32 does not go with it. Some students will think because there's a negative on the 32, that'll make it drop down. No, that's just for exponents, not for regular old numbers. So that would be the answer to number 5. All right, looking at number 6. Notice that this 4 is not in the parentheses. So this 4 will not be affected by the negative 3 power. This is that situation where we have a power to a power. So this is when you multiply. So this will be multiplied by both of these exponents. So this 4 is just going to sit here for a moment. Okay, so I'm going to have the 4 still there. But so multiplying, I'm going to get n to the 6th power, and then p to the negative 18th power. Okay, so I've got that now. I really don't need the parentheses. I don't know why I copied that on down. Now that we did the 3, parentheses are meaningless. So we have this. Now, what is going to move and what is going to not move? Be very, very careful. Here is the invisible fraction line. This is the only thing that's on the wrong side of the fraction line. So it is going to move down, but the 4 and the n to the 6th power are going to stay up where they are. So your final answer is going to be 4 n to the 6th power over p to the 18th power. Once I move it down, it's positive exponent. Okay, so there's number 6. Number 7. All right, there aren't even any negative exponents on this one, so it should be Muy fácil. Okay, let's see. I see the w. There's nothing really with the w, so the w squared is going to remain unchanged. Looking at the x values, the 6 x's in the bottom are going to cancel out 6 x's in the top. So this is going to leave x to the 6th power. You know, let me emphasize this just one more time in case this is new to you. Notice I'm not dividing 12 by 6 and getting 2. That's because looking at these x's, here's what's really happening. Okay, and I encourage you not to draw this out, but this is what you should be thinking in your mind. X to the 12th power is really 12 x's being multiplied together. Alright, x to the 6th power, of course, is 6 x's being multiplied together. So what we are doing when you have the same things in the numerator and the denominator is they divide each other out. So the 6 x's in the bottom cancel out 6 of the 12 x's in the top, and that leaves 6 x's in the top, which I will write as x to the 6th power. Yes, you know, a shortcut is to think of this as subtraction, 12 minus 6, but trust me, there are all kinds of problems that are created when students just blindly think of it as subtraction. It's really canceling out, and it'll make it more obvious where the result goes, numerator or denominator, and that's the big problem. Students forget where things go, and they'll want to put negative exponents everywhere. Think of it as canceling, and you will thank me. Okay, now looking at the y's, okay, again, thinking of it as canceling out. We have 2 y's on the top and 8 y's on the bottom. These 2 y's are going to cancel out 2 of these y's. So that's going to leave 6 y's. But it is clear that those 6 y's will be on the bottom, because that's where there are more. That's where the leftovers will be. And then there's z to the 4th power that doesn't go with anything, so we just bring it down. So that's it. That would be the answer to number 7. All right, number 8. Okay, anything to the 0 power is 1. So which means this entire expression, this n to the 0 power, is worth 1. And 6 times 1 is still 6. So I really can just scribble this out. Alright, it will not change the other n at all. I like to go ahead and move around everything that has a negative exponent at this point. So I see this p to the negative 3 power. That's going to go up and become p to the 3rd power up there. I see this n to the negative 5 power. Okay, that's going to drop down and become n to the positive 5 power down there. Alright, so essentially this is what we have at this point. Okay, so my 18 and my 6 and my p to the 12th power, those are all things that are not going anywhere. No negative exponents. Alright, my p to the negative 3 power went up and became positive. My n to the negative 5 power went down and became positive. So this is what we have so far. Now we can go ahead and put things all together. Let's start by reducing this. 6 goes into 18 3 times, so that'll be a 3 here at the top. The n's, all I have is n to the 5th power, so I'm just going to write that, copy it down. And these p's, this is that second situation that I reviewed for you. This is where you add the exponents, so this is going to be p to the 15th power. So that is it. Alrighty then. Looking at number 9. This one's a little bit strange. We've got to be careful. There's more than one way to do it, but here's the I think is the easiest way to follow. If it weren't for the -3, okay, that's the thing that kind of confuses people. This would be like a problem that I did above. This is a power to a power. Both of these are a power to a power. So I'm going to wind up multiplying these. So this is going to give me n to the -8th power, and this is going to give me p to the +10 power. All right? This is the one where you multiply. Now, but what to do with the -3? If this were a +2 power, then I could just square it and get 9. But with it being a -2 power, you know, some kids will think that you just change the sign. No. This being a -2 has no effect on whether this is positive or negative. Negative exponents drop things to the other side of the fraction. So here's what I recommend. Just for a moment, you're welcome, sir. Just for a moment, just stick the -2 power on it. All right, just write -3 to the -2 power, just like that. And then we'll just deal with it later. And in fact, we'll deal with it now. Because what happens next is, here is our invisible fraction line. Everything with a negative power is going to get dropped down. So you see the p to the 10th power, that's going to stay where it is. But the n to the -8th power, that's going to drop down. But guess what? The -3 to the -2 power, that's going to drop down as well. So what we will have is this. The p to the 10th power stays up. P to the 10th power. N to the 8th power drops down and becomes positive. And this -3 to the -2 power drops down and becomes positive as well. So this is almost the answer. Now that we don't have a negative exponent anymore, now we can go ahead and do it. We can square it. Okay, so the final answer is going to be p to the 10th power over 9 n to the 8th power. Obviously, a negative times negative is a positive. That's why it became a +9. All right, that one was a little tricky. I hope you followed it. Number 10, we have this w to the 0 power. Let's just take care of that right now. Okay, anything to the 0 power is 1. But 4 times 1, I mean, you know, -4 times 1 is just -4. So that's just doesn't do anything. So it's basically, you can just scribble it out. Let's move everything that has these negative exponents. So look, it's kind of like this. The -4 is not going anywhere. The w to the 3rd power is not going anywhere. The x to the 6th power is not going anywhere. None of those have negative exponents. Now, everything else is going to move. So the x to the -2 power, okay, that's going to go up and become x to the +2 power. Okay. The y to the -9 power, that's going to go up and become y to the +9 power. The y to the -3 power is going to go down and become y to the +3 power. Alright, so those are all the motions, but everything in blue here just stayed where it was in the first place. No negative exponents. Again, do not move the 4 because it's negative. It's just exponents that move. Okay, so now we can go ahead and simplify the problem. So -4, so we'll just have -4 here. The W, there are no other W's, so this is just going to stay W to the third power. The X's, we can put these together, and that's going to make X to the eighth power. Alright, this is the case where you add when the variable appears twice. And the Y's, I have 9 Y's in the top and 3 Y's in the bottom. So the 3 Y's in the bottom are going to cancel out 3 of the Y's in the top. So that's going to leave 6 Y's in the top. So this will be the final answer for number 10. Alright, there appears to be a second number 10, but that is obviously a typo, but we're just going to roll with it. So given the parent function, 1.5 to the x power, what is the transformation caused by putting a negative 2 up here? Adding or subtracting a number in the exponent, these are left and right motions. Okay? These left-right motions are always the opposite of the way they look. So instead of going to the left 2, the way it kind of looks, this would be a translation to the right 2. Alright, looking at part B, what is the change that's caused by sticking a negative in front of a function like this? Well, that is a reflection over the x-axis. Reflection over the x-axis. Alright, basically the function is turned upside down. How would you transform the graph to produce this function? What's caused by putting a negative 3 on the end of the function like this? Numbers on the end of the function, these are always up and down motions, and these ones work just the way you would think. Negative moves you down, positive moves you up. So this is a translation down 3. Alright, moving on. Now we need to solve for x. Solving these exponential equations. Now the trick for this first one is to write this as a fraction. Now you should have learned in elementary school that 0.1 is the same thing as 1/10. So this is 1/10 is equal to 100 to the, why did I put negative x? 100 to the x minus 4 power. If for some reason you see a decimal that you don't know the fraction for, you can put it in your calculator. You know, if you put 0.1 in your calculator and hit the toggle button, it will give you the fraction. Now we need these bases to be the same though. So I see the 10 happening, and I can write 100 as 10 squared. So I can rewrite 100 as 10 to the second power, but I have to put this x minus 4 kind of in parentheses. And 1 over 10 is the same thing as 10 to the negative 1 power. So now we have bases that are the same. Okay, so it's like 10 to the negative 1 power. This will be 10 to the 2x minus 8 power, because you have to do the distributive property. If the bases are the same, the exponents will be the same. So that means negative 1 should equal 2x minus 8. Okay, and then we can add 8 to both sides. So that's going to give me 2x is equal to 7. So then the last step is just to divide both sides by 2. Oh, I missed. Dividing by 2, these cancel out. So your final answer is x equals 7 over 2. You know, just leave it as a fraction. So that's number 11A. Okay, looking at B. Again, we need these bases to be the same. I'm going to have to change both of these numbers, because you can't write 64 as like 16 to a power. But what we can do is write both of these using base 4. So for example, 16 is 4 squared. And then of course I'll have my x minus 3 still. But 64 is 4 to the third power. Memorize that if you haven't already. And then I have the x plus 5. So now I have the same base. That's what I need to be able to do the problem. So this is going to be 4 to the 2x minus 6 power, a little distributive property there, is equal to 4 to the 3x plus 15 power, distributive property again. If the bases are the same, the exponents are the same. So I can go ahead and write 2x minus 6 is equal to 3x plus 15. Easiest thing to do now is just to subtract 2x from both sides. So that's going to give me negative 6 is equal to x plus 15. Then I can subtract 15 from both sides. Running out of space, but you get the idea. And so those go away. So that's going to give me negative 21 is equal to x. So that is the answer to part B. All right, last two questions. The graphing, last part of the review. Exponential functions are functions that have asymptotes, these lines where the graph gets closer and closer but never reaches. This number at the end here tells me what the asymptote will be. So there will be an asymptote at y equals 3. So we should go ahead and draw that as a dotted line. I think I'll make it blue. So this is going to be the asymptote. Okay, for the rest of it, I'm just going to put this in my calculator. Okay, turn to your TI-30 XS Multiview. Hit the table button, of course, and then just start typing it in. So we'll have negative, parentheses, 1/2, close the parentheses, to the x power plus 3. So there's my x power, get out of there, plus 3. So just type it in. Okay, you can start at 0, it doesn't matter, we'll scroll around. Now, some students have trouble understanding which values to use, but the bottom line is we're going to use the ones that fit on a normal graph like this. I have a 10 by 10 graph, so anything bigger than 10 is not going to fit. So for our purposes, we're looking for things smaller than 10. Now, as I go in this direction, see where the big numbers come in? Well, bit large in absolute value, ignoring the negative sign. Negative 29 will not fit on the graph. Negative 13 is close, but it doesn't quite fit on the graph. So this is the first value that's going to fit. So this is going to be the first value on my chart. So negative 3, negative 5. Okay, so I'll go with negative 3, negative 5. Which means that then I'm going to have negative 2, negative 1, 0, and 1. So let's get the y values that go with them. Alright, so next I have negative 1, 1, and 2. And that last value is 5 over 2. Alright, which of course is 2.5. Notice your calculator will show that if you highlight it and hit the toggle key if you need it. So this is 2.5. Alright, let's go ahead and graph these values and see how the curve looks. So negative 3, negative 5 would be here. So here's negative 3, comma, negative 5. Negative 2, negative 1. Negative 1, comma 1, 0, comma 2, and 1, comma 2.5. So you see the curve bending in this direction. And as I mentioned, it's going to get closer and closer to this asymptote as it goes to the right. So it's important that you follow through. Alright, don't stop your graph here, continue it on. Now by the time it gets over here, it's going to appear to trace the asymptote. So in your mind, you have to understand that it's really not touching. It just looks like it is. Okay, and you need to extend your graph in the other direction as well. Alright, so make your graph go all the way to the edge of the graph. So that's what your graph should look like. If you want to put some arrows on the end, so much the better. Now the domain. This graph goes left and right forever. So like all exponential functions, the domain will be negative infinity to positive infinity. The range, always give the range in order from bottom to top. So this will be negative infinity here at the bottom, up to a height of 3, the asymptote, negative infinity to 3. Even though the graph never actually gets to 3, we can show it by using parentheses instead of a square bracket, meaning everything up to 3 but not including the 3 itself. The y-intercept. Y-intercept is always going to be 0, comma something. So there it is, 0, comma 2. The asymptote. We knew from the beginning that the asymptote would be y equals 3. Please do not just put 3. It has to be y equals 3. Okay, that is how you do that. Last problem of our review. Now, for problem B, notice how there is no number being added or subtracted on the end. Like this one has a plus 3, this one has nothing. So that tells me that the asymptote is y equals 0. Alright, in other words, the x-axis itself is the asymptote. So I will just go ahead and put a dotted line right on the x-axis. Let's go ahead and type this into the calculator. Alright, using the table function. So it looks like we have 2 times 3 to the x minus 4 power. Doesn't really matter where you start because we're going to scroll around anyway. Right, 2 times 3 to the x minus 4 power. Alright, again, look for the big numbers. The big numbers. Alright, this time the big numbers are at the bottom. 18 will not fit. Okay, 6 is the first value that fits. So 5, 6 should be the first value on your chart. Okay, and I like to keep it. So if we put 5, 6 at the bottom of the chart, just like it is on the calculator, and just go in order from there on up, we'll wind up going from 5 back to 1. And these are the y values that go with them. In the TI-30, they're giving us fractions, okay, but you can convert any of these fractions to decimals by highlighting the fraction and hitting the toggle key. And I'm just rounding to the nearest tenth. So that's where, for example, I got the 0.2 from. So let's go ahead and graph the points and finish this up. So 1 is 0.1, which is essentially going to appear to be right on the line. And 2 is 0.2. That's just ever so slightly higher. 3 is 0.7. Alright, so that's most of the way up to 1. And then 4 is 2. And 5 is 6. Alright, so these are the values that you should have graphed. So you can already see that it's at 0.1, so certainly all the rest of this way on the graph, it's just going to appear to trace the asymptote. Okay, it's going to appear to be right on the line, but in your mind, you know that it's really 0.01, 0.001, and so on. And then we just go from there. Okay, so your graph should look something very much like this. Alright, now let's answer the little questions that go with it. The domain, as always, will be negative infinity to positive infinity. The range, always give me the range from bottom to top. This graph has a floor. The asymptote is at 0 itself, but it goes up forever. So 0 to infinity in that order. 0 to infinity. Even though the graph doesn't actually reach 0, it just gets closer and closer to it, we can still use 0 as the bottom of the graph as long as we use parentheses instead of a square bracket. Parentheses means everything up to 0 but not including 0. The y-intercept. Okay, this is the y-intercept is going to be found on the calculator. Okay, we know the y-intercept is always 0 comma something, and right now 0 is not being included on my chart. So look at your calculator and just scroll up to 0, and that'll be the y-intercept. So the y-intercept is 0 comma 2 over 81, and you might as well leave it as a fraction. You know, if I toggle this, that's like 0.02, and you might be tempted to round that to 0, and I really don't want you to put 0. So we'll just use a fraction on this one. So 0 comma 2 over 81 is what it really is. Okay, that's the y-intercept. And finally, the asymptote we knew from the beginning was y equals 0. Please don't just put 0, put y equals 0. Alright, that's it for our review. This video is almost an hour long, so it's really way too long. But when you're reviewing an entire unit of exponents and exponential functions, it's just hard to get that done in 30 minutes or less. I really hope this review of exponents has been helpful, and if it has been, a like, a thumbs up is always appreciated. Either way, I will see you on the next video.